My name is Tim. I'm a data scientist on the Lyft mapping team. And today I'll be going over the process we took over the past 5 or so years to build our own navigation system on top of OSM. So a lot of work has gone into this, starting with building a map or a road network on top of OSM, as well as collecting different components or data sources for that map, such as real-time map data and the routes and navigation system, as well as many other components not listed here. So today, we're primarily focused on the routing portion, specifically how we leverage map data from OSM to provide high-quality routes, as well as how we use the routing data we get and driver compliance data to update the map in the feedback loop between the map and our routes. So first, I'll start by how we built the routing algorithm and how we added more map data to get better performance. So yeah, some routing 101 for those who are new to this area. First, you have to start with a road network. So obviously, we get ours from OpenStreetMap. It's pretty high quality. And two, once you have a road network, you should define the cost for traversing each edge in that road network. And third, there are many tools you can use to compute the minimum cost path through that road network. So in this case, if you're starting on node A and going to node F, there's 3 different paths you could take. And the challenge here is we want the path with the lowest cost to be the one that drivers want to take. And so that's kind of the challenge we face in creating good routes. So there's 2 different components that that represent the main challenges. One is understanding the legality or possibility of certain maneuvers. So things like turn restrictions, road geometry that just doesn't allow for you to make different turns. And these are addressed through understanding and improving the map, as well as applying high costs to illegal or impossible maneuvers. And then the second, which is a bit more challenging, is how do we understand driver preferences? So what things in the physical world do drivers try and avoid? And how can we use those things to create accurate segment and turn costs? And this we address through a machine learning approach to understand what map data features actually inform how drivers navigate throughout the world. So yeah, when we first started this process, we started with maybe what you would think as the simplest algorithm, which is just defining the cost of a segment as the time it takes to traverse that segment. There's different ways you could define travel time, such as using real-time traffic observations, historical traffic observations, so how fast do people drive over the past month or week of data. Or if you don't have observations, you could use speed limits or road classes to infer how fast people might drive. But yeah, this approach wasn't perfect. There's a lot of problems with only using travel time. So yeah, where you have sparse data in more rural areas, you might not have accurate speeds. And a lot of literature shows that travel time does not capture driver preferences. And the main theme is that balancing travel time, basically we need to balance travel time with route complexity. So on the right, you'll see 2 examples. In the top right, there's a route with lots of different turns. And most drivers would prefer something simpler. And then on the bottom, you'll see a route where we suggest the driver get off the freeway and then back on to avoid a traffic jam. And while that might be faster, most drivers aren't going to comply with that. So yeah, the question we asked ourselves is how can we use machine learning and incorporate all of the wonderful features we get from OpenStreetMap? So yeah, a simple way to illustrate this is, let's say we want to add one more feature to our cost. So say we care about time and distance. If we apply different weights to time and different weights to distance, essentially we could ask questions like, okay, drivers will take a shorter distance route but longer time route if those 2 factors are favorable. So for example, if a route is a mile shorter and only adds a minute, you might take the shorter distance route. But if it's a mile shorter and 10 minutes longer, you are obviously going to take the faster time route. So these weights tell us how much we can trade off time and distance. And then, yeah, we can add more map data features. So things like road classes, turn categorizations, like left or right, and a bunch more features we can add. And again, the same sort of trade-off applies. So a U-turn is only worth it if it saves some amount of time. And the way we learn these weights is through machine learning. We started with a simpler approach that was inspired by a paper from Bing Maps. Essentially, we could start with certain weights. So say the weight for time is 10 and the weight for distance is 5. We could generate routes using those weights and see what they look like. Do they match what drivers actually did, or should we keep iterating? And eventually, we follow this loop until the weights are able to mimic what drivers do in the real world. But there are some limitations of this approach. First, it's very slow. So in this feedback loop, we have to run our routing engine on every iteration, which takes a lot of time. And we're training these models on hundreds of thousands of routes. And essentially, it limits the number of features we can include because, yeah, if you add more parameters, it widens the search space, which increases the training time. And also, it's only a linear model, which fails to capture interactions between different features. So for example, a left turn on a one-way road might be less difficult than a left turn where you have to cross traffic. Also, this example on the right, if you start in the top right and you're trying to go to the bottom left, crossing that major road in the middle, there might be different intersections you would prefer or that are simpler to cross. So you might prefer to take a right turn at a stop sign and then a left turn at a traffic light. And these, basically the entirety of the intersection, so things like the directionality of the turn as well as the traffic control elements, impact what drivers prefer. So kind of where we're at now, we want to capture more complex driver preferences through more advanced machine learning approaches. So the idea we've been exploring is learn to rank. Basically, the idea is we can run our routing engine at the start of training rather than doing it on every iteration, and score or rank those routes that we generate based on some criteria. So on the left, that's an example in San Francisco where we generated 5 routes, and we might rank them in some way. So basically, the green route and the red route that are the more extreme routes, probably drivers aren't going to take them, so they'd be the worst ranked routes. And then during training, we can use a typical learn to rank approach where we compute the cost for all generated routes based on the current set of weights. And we can ask, does the cost-based ranking match the ranking we got in pre-training? And we're trying to learn a function where the routes that drivers prefer or are ranked the highest have the lowest cost, so that when we see that route in real time, that route will be generated as it has the lowest cost. So for this example, you can see in the bottom right, initially we started with the 4th ranked route as the lowest cost. But as we run this procedure, we're able to switch around the costs of the routes so that it more closer matches the ranking. And this allows us to use nonlinear models, basically the whole, all standard machine learning techniques, which we couldn't use beforehand. So that's where we're at. The next thing I'd like to do, so we've incorporated all these map data features into our routing cost function. And now we can look at where things might go wrong and how we can use driver behavior to improve our map data. So how does map data impact routing? One, the connectivity and geometry of the road network, which illustrates what's possible. 2, the static attributes of a road segment, things like street names, lane level data, road class. And 3, the dynamic attributes, so road closures and traffic, which I don't touch on too much in this talk. And how can we fix map data issues? One is user feedback. So we give a route to a driver. they don't comply, they have the option to say, I didn't like my route, and we can investigate. And 2 is automatic detection. And so I'll give a few examples. The first is a case of a road connectivity issue in Boston. So here we recommend a U-turn on a motorway. The driver is located in a tunnel, and actually on the bottom right you can see that the tunnel is connected to a surface level road, and we recommend the driver to make a U-turn, which isn't even possible. That was recommended 200 times per month before we made the fix. This is quite close to the conference center, but this road has had its highway tag changed 5 different times from residential to service road. And the driver is asked to turn right into this narrow alleyway. And if you miss this turn, you can see in the bottom right, there's a long detour to get back to where you need to go. In May, so just this past month, we recommended this maneuver 2,400 times with a 50% compliance rate. And in January, when we first noticed this issue, we recommended it 0 times after we updated the tag. But there's a large debate about residential and service roads. So this is just one example of how different standards could impact routing. So moving on to more automatic detection schemes. Here's a case that we saw quite a bit where we're asking the driver to turn right, but we tell them to use the middle lane to turn right instead of using the turn lane. The reason for this is because the turn lane is modeled as a different segment. It could be modeled as 2 right turns as opposed to just 1 right turn, or the segment could have slower speeds because drivers have to slow down to make the turn. So we built some custom geo patterns to detect these kinds of graph elements. And we're able, in some cases, to update the geometry of these segments in OSM. And in other cases, we have to add turn restrictions in our own map to ensure that drivers are told to use the turn lane to make these types of turns. This impacted about 4,000 intersections. So this was, quite a big issue for us. Another way, which a lot of people have contributed to and has reached maturity now, is using driver feedback, or basically automatic feedback. So we recommend millions of maneuvers each day. Sometimes drivers don't comply with those maneuvers, but we can say, okay, when we recommend this right turn on this road, drivers have a 25% compliance rate, which is quite bad for us. So if we look at maneuvers that have the lowest compliance, or also the largest consequence, so how much time is added to your trip if you miss this maneuver, we can sort based on those criteria and investigate. So one example that's very tricky for rideshare is gates. And since January 2025, we made about 3,000 edits to OSM to say which gates are open, which gates are closed. And you can imagine in rideshare, the person who's navigating doesn't exactly know which gates they can use to pick up the passenger. So it's a very important issue for us. Here's an example on the right of a gate that was accidentally categorized as closed, even though it's open. In conclusion, we've had a great partnership with OSM. We bet on OSM in 2020 to power our map, and it's currently used in 90% of rides. I've been told that's closer to 95% now. And in the last 12 months, we've made about 160,000 edits to the map, giving back to the community. And some challenges, as you saw, sometimes OSM standards might not perfectly suit the routing use case, such as intersection geometry and road class definitions. Thank you for listening. There's a Lyft table over there with others who have contributed to this work. And I think we have maybe time for one question.
Yeah. Do we have any questions? Please welcome to the microphone. We have one.
surprised I'm the only one with a question. I'm just curious how, if you have any interesting experiences clashing with other editors, whether it's individuals or like another company that's doing the same thing you're doing.
Yeah, nothing that I'm aware of. So we do have a large curation team, which makes most of the edits. And yeah, on the routing side, we kind of identify where we might think OSM edits might be made. I do know, yeah, there are some cases where we're not able to make the edits we want based on OSM standards, and also cases where, yeah, things change back and forth. But yeah, in general, I think we found that OSM has been a pretty useful tool for us. Yeah, thanks all.
Thank you very much.